Am I audible to all of you? Just write in the chat box. Okay. So I am sharing my today's presentation. Just a minute. All of you clearly see the presentation on your screen. Just write in the chat box. Okay. So today we are going to start Unit 3 of Compiler Design. As you can see on your screen that the Unit 3 is basically syntax directed translation. So what does the syntax directed translation means? As you can see, the syntax directed translation, which is abbreviated as SDT, is the combination of CFG and the semantic rules. So CFG, as we already studied in the unit 2 and also in the theory of computation subject, now here semantic rules are new uh, in this unit. So the semantic rules are further classified into two forms like syntax directed definition and syntax directed translation schemes. Now the syntax direct, directed definitions are further classified into synthesized attributes and inherited attributes. So you just need to remember that the semantic rules are classified into two forms, and after that the syntax directed definition are further classified into the syntax synthesized attributes and inherited attribute, because these types of attributes and their comparison is important. Now moving further, now let's discuss the definition of semantic analysis. As we already studied the lexical analysis and the syntax analysis. Now, in this unit, we are going to study the semantic analysis. So, the semantic analysis means it validates the meaning of the code by checking that the sequence of the tokens is meaningful and correct, is associated with the correct type, and is consistent in the way in which control structures and data types are used. It means that if our data type is int type, then we are going to calculate only integer values. We cannot calculate or we cannot have the character values if we have a data type is of int. In the same way, if our data type is of character type, then we can uh, evaluate or calculate only the character values. So the semantic analysis deals with it. Okay. Now I am enlarging the screen. Just a minute. Just a minute. Now it's visible to all of you. Okay. Now I once again discuss the semantic analysis it is the the third phase of the compiler design. So the semantic analysis, it validates the meaning of the code by checking that the sequence of the token is meaningful and correct, is associated with the correct type, and is consistent with the control structures and data types that are used. So, as an example, if our data type is of integer type, then we only evaluate the only the integer values with it and not the character values. In the same way, if we take our data type as the character, then we calculate only the character values with the character data type and not the integer values. So the semantic analysis deals with it. Now moving further. Now the semantic analysis involves. So these are the functions or the roles the semantic analysis uses. The semantic analysis involves in the type checking, then the label checking, then uniqueness checking, then the control flow checking, and name related checking, etc. So these are some of the roles or the functions which are performed in the semantic analysis. Now the semantics of the language is validated with the help of semantic rules. So there are certain rules which are called as the semantic rules by which we can uh, we can justify the language semantically. So semantics can be static or dynamic. So let us see what does static and dynamic means. There are some other students waiting in the lobby, so I am just allowing him just a minute. Now let us discuss what does this the static and dynamic semantic means. Now the static semantics of a language is related to the meaning of the program that can be checked at the compile time. As we already see that the at the compile time, whatever is done, it is known as the static. And in the case of dynamic semantics, refers to the meaning, expression, statements and other programs that can only be checked at the runtime. So whatever we checked at the runtime, whether it will be the expressions, statements, and their meanings in the program at the runtime, that is called as the dynamic semantics. So in the diagram, as you can see that the the second phase after the parser, mm, the abstract syntax tree is formed, and the abstract syntax tree is the input to the checker, means the syntax directed translation. And after the syntax directed translation, the abstract tree converted to the annotated syntax tree, because here we already checked the semantics of the language or the semantics of the parse tree. So this is called as the annotated syntax tree, and this annotated syntax tree is the input to the intermediate code generator, which is the basically the fourth phase of the compiler design. So just remember this diagram, that after this phase, we convert the abstract syntax tree into the annotated syntax tree. Now let's check the applications of the syntax directed translation. So this type of question can be asked in your university exam of basically is of 2 marks. So like what are the applications of syntax directed translation? So there are certain applications of syntax directed translation. These are: first is the evaluating arithmetic expressions, then creating syntax trees, then converting inputs to prefix, then converting infix to postfix, then generating the intermediate code as we already see in the previous diagram, then converting binary to decimal, then storing type information into symbol table after the semantic analysis. So these are some of the applications for which we are using the syntax directed translation. So just remember these applications. So all of you understand it till now? Just write in the chat box so that we can move further. Okay. Now the semantic analysis can be performed by adding some information to the existing grammar. As we already see in the first diagram that the CF after the CFG we need to add something to the semantic rules. So the CFG is extended by associating set of attributes with the grammar, symbols, and a set of semantic rules with the productions. So it is just the definition. So moving on. So semantic rules. So now we are going to study the semantic rules. So semantic rules specify how the attributes of the grammar symbol of the production are manipulated. So these are the rules which specify how the attributes of the grammar symbol perform in the syntax directed translation. So two notations are used to associate the semantics with the production. So these are the syntax directed definitions and the translation scheme. So as we already discussed in the first diagram of this unit, so we are going to study the syntax directed definitions. Now the syntax directed definition, so they are high level specifications for translation which hide many implementation details from the user. So the user need not to specify the order in which the translation takes place because we are hiding the underground or the details from the user. So in syntax directed definition, we are hiding the implementation details from the user. So now the translation scheme. So the translation in the case of translation stream, they indicate the order in which the semantic rules are to be evaluated. Whereas in the case uh, of syntax directed definition, they are hiding it from the user, and we are and the user is not going to bother about the order in which the translation takes place. But in the case of translation scheme, they indicate the order in which the semantic rules are to be evaluated. So both in syntax directed definition and translation schemes, the input token string is passed, the parse tree is built, and then the tree is traversed as needed to evaluate the semantic rules at the parse tree nodes. So we will take an example of this later. So just remember that after the syntax directed definition in the translation scheme, a parse tree we need to form a parse tree, and in that parse tree we are going to check whether it is semantically correct or not, and if it is not, then we need to balance it semantically. So moving further, so the two types of attributes supported by syntax directed definitions are the synthesized attributes and the inherited attributes. So these type of attributes are very important. So let us discuss each of these attributes one by one. So first are the synthesized attributes. So an attribute is said to be synthesized attribute only if its value is calculated in terms of its children in the parse tree. It is the definition. So only the attribute is called synthesized attribute only if its value is calculated in terms of its children. So as you can see as an example here, um, if you are given a production like A produces B, C, D, then you need to make a parse tree in which A is the parent. Here A is the parent node and B, C, D are its children. So you can evaluate it with like this, like AI means some is equal to a function of its children. It can be one children or it can be many children. So the value of the parent can be evaluated from its children. So here the parent A obtain its values from the child nodes, that is either from B, C, or D. So such type of attributes are called as the synthesized attribute because the parent value, because the parent node got its values evaluated from their children only. That's why they are called as the synthesized attributes. Now let us check the inherited attributes. So, as its name suggests that you all already studied in the OOPS that in inheritance concept is there. So, as its name suggests that inherited attributes means an attribute is said to be inherited only if its value is evaluated in terms of its parent or children or both in the parse tree. As an example, as you can see here, that a same production is used. A produces B, C, D. Here, parent is A, and its children are B, C, D. But we can also evaluate. Here, you can see here certain evaluations are taken place. In the first case, if we are going to evaluate Ci with the value of AI, means the value of parent is going to decide the value of its children, one of its children. It is correct, and also you can see that um, the value of CI is also being calculated from one of its siblings, because as you can see here on the right hand side of the production BCD is there, and we are going to calculate the value of C attribute C, and the value of attribute C is going to be calculated from the value of attribute B, because B is the left hand side attribute of C, so it is possible, because B occurs or before the C. So when we reach the C, we already passed the B value. So it is this is possible. But in this case, as you can see here, the value of Ci is going to be calculated from the value of its other attribute D, which is another sibling of C, but D occurs at the right hand side, but D occurs after the C. So this type of calculation is not possible because we are evaluating the value of C and from the value of D, but C occurs before D, because C is exists on the left hand side of D. So this type of evaluation is not possible. So here, in these example, as you can see here, here C is inherited value from its parent A and also from its sibling B, and C cannot inherited its value from its sibling D, because D occurs at the right hand side of C, and C occurs before D. So in that case, the value of C does not depend on the value of D. So all of you understand it till now? Just write in the chat box because this concept is very important. So in the case of inherited attributes, the attributes can take the value from their parent as well as from their left siblings, and not from their right hand side siblings. Whereas in the case of synthesized attributes, the parent can take their values evaluated from their children's only. So these attributes are very important. So moving on to the next topic. Now the next topic is types of syntax directed translation. Means S attribute syntax directed translation and L attributed syntax directed translation. So we are going to differentiate these S attributed syntax directed translation and L attributed syntax directed translation. So in the case of S attributed SDT, it uses only synthesized attributes. We already studied it. For example, if for a production A produces BCD, then the value of A is only dependent on its children. Like the value of A depends only on either B, uh, or C or D or their combinations. Whereas in the case of L attributed SDT, it uses both synthesized and inherited attributes. So each inherited value is restricted to inherited either from its parents or left sibling. As we already discussed it in the previous topic. Like if we have the production like A produces B, C, D, then if we need to calculate the value of B from the value of its parent, then this is possible. If we are going to calculate the value of C from its other sibling, like from D, so this is not possible. Why? Because D occurs after C. Uh, that is on the right hand side. So this is not possible, and hence it is written as the false. And the third type is if the value of C we are going to calculate it from B, then this is possible because B occurs before C, as B is on the left hand side of C. So that's why we can calculate the value of C from the value of B. So just remember it. S attribute SDT uses only the synthesized attributes, whereas the L attributed SDT uses both the synthesized as well as the inherited attributes. So this is the first point of their difference. Now moving on. Now the second point is in the case of S attributed SDT, here semantic actions are placed at the right end of the production. As you can see here, the production E produces E plus T, and here on the extreme right, we are going to write the semantic actions like E dot well equal to E dot well plus T dot well. So semantic actions are written at the right end of the production. Whereas in the case of L attributed SDT, here semantic actions are placed anywhere on the right hand side of the production. So here we can write the semantic action anywhere on the right hand side of the production. Like if we have the production A produces BCD, then this semantic action can be right at the right end, or this semantic action can be right in between C and D, or it can be right between B and C. So it can be written anywhere on the right hand side in the case of L attributed SDT. Now the third difference. So in the case of S attributed SDT, here attributes are evaluated in a bottom up manner. So if we have the production A produces BCD, then for calculating the value of A, which is the parent, we need to move from bottom up. from the childs to the parent. So this follows the post-order traversal of the parse tree. Whereas in the case of L attributed SDT, here attributes are evaluated in depth first and left to right order. Means you need to just concentrate on how we are evaluated. We are moving from A to to its left, means B in BCD, B is at the leftmost, so we are moving from A to B. Just concentrate on the arrows. Then we are moving from B to C. Then we are moving from C to D, and after that we are again coming to the A. So we are following the depth first and left to right order. So this type of order is also known as the pre-order traversal of the parse tree. So traversal of parse tree you already studied, or the traversal of tree you already studied in your data structure and algorithm subject in the trees unit. So just follow it. So as attributed, SDT follows the post order traversal of the parse tree, whereas L attributed SDT follows the pre order traversal of the parse tree. So just remember this difference between the S attributed and L attributed SDT. So all of you understand it till now? Just write in the chat box so that we can move to the next topic. Just a minute, other students are getting it or not? Gunjan, Harshita, Kiran, Parshit Kothari, are you getting it or not? Just write in the chat box. Okay. So moving uh, to the next topic. Now the relationship between the S attributed SDT and the L attributed SDT. So as you can see in the diagram that S attributed SDT is in the inner circle, and after that L attributed SDT is there. So if there are 2 points which comes from this diagram, that if the definition is S attributed, then it is also L attributed, because S attributed SDT is in the inner circle of the L attributed SDT. As the L, and the second point is, as the L attributed definition encloses the S attributed definition, but vice versa is not possible. So if we have the L attributed definition, then it can be that L attributed definition can be S attributed SDT, or it can be not. But if it is S attributed SDT, then it is surely L attributed definition as well. So just remember this diagram. So moving on to the next topic. Now, what do you mean by the semantic action? Now there are certain points related to the semantic action. So they are the fragments of codes that are embedded within the production bodies by the syntax directed definitions. They are usually enclosed within curly braces. They can occur anywhere in the production but are usually found at the end of the production. So in the just remember these points, and we are going to discuss some numericals which are based on this. So the first numerical is, we are going to calculate the infix to postfix conversion. So here, as you can see in the table, on the left hand side, productions are there. These are the productions are there. Like five productions are there, and corresponding to in the corresponding rows, their actions are there. So as you can see here, E produces E plus T. So here the right hand side E is different from the left hand side E. So that's why it is written as E produces E1 or E dash plus T. And here the action is the print action. Print plus sign is there. As you can see clearly that plus sign is there. Then the second production is E produces T, and the action is performing as the braces. Only the empty braces is there. Then the third in the third production, T produces T dash or T1 into F, and here the action performed is we need to print the into sign. And then the fourth production, T produces F, and the action we are going to perform is the empty braces. And the fifth production is F produces num. Just num means the number, the numerical digits. So in that case, we are going to print the let's dot well, means we are going to print the number value. So these are the productions given to us, and corresponding to the production, we are given the actions we are performing corresponding to that productions. So and the input is given to you, that 3 plus 4 into 5. So these are given in the infix form, and after this we are going to convert it into the postfix form. So just to see how we are going to solve this and convert it into the postfix form. So just remember these productions and the actions, corresponding actions. So, and just remember the input given to us, 3 plus 4 into 5. So as you can see, I think there are some difficulty in seeing this, but I am just drawing it here parallelly, that the first production is E, and it produces E plus E dash plus T. So we are going to return as E dash plus T. After that, there are certain productions from which we are going to move from E produces T, and after that from T produces F, and from F we get the num value. So after we are reaching the num, then we can write the numbers. So first number is 3, and now we are going to because in the infix we have 3 plus, input is given to us 3 plus 4 into 5. So we need to reach at this point, 3 plus 4 into 5, by drawing it. So the plus sign is there, then we need to have also the into sign. So into sign we can got from T produces T dash into F. So after that, we can use the production T produces F, and from F we have the F produces num, and from this we can reach that num. Here the second value is 4, and from here F we get the F produces num, and from here we get the value 5. So this is the parse tree we make from the following productions, and now we are going to take the actions which are corresponding to those productions. So as we are moving it from the top, and we are following the depth most and the left to right traversal. So just to see, I am following the path, I am following it, and I am going to reach it to 3, means the last one. And now I am moving up till I reach the plus symbol. Then I am passing it, and just I am moving it to the second one, the second trail, and I am just following it because I am moving depth first and left to right I need to follow. Then I am just following it, and after that I am just following this into sign. Then I am following this third trail, and I am following this, and after that I am reaching F again, and after that I am reaching T again, and after that I am reaching the route again. This path I need to follow. So as I am traversing this path, so I need to as I am traversing this, so and now I am going to evaluate it side by side. So in the first case I am reach at the 3, which is a number, and after that, the as you can see here, this plus sign, it cannot be taken, or because the second operand is not yet traverse, or not we are not getting the second operand till this point. So we are just following the path, and after that I am getting the second number, which is the 4, and after that I am just moving upward, and I am just getting this into is not evaluated because I am again not getting the second operand here. So I am just following it, and after that I am getting the number 5, and now I am getting all my 3 numbers, and after that I am reaching here. So at this point I am reaching here, and now I am moving forward to this, and I am reaching here at the point of T here. So at the point of T, as you can see here, the value of T can be evaluated from the value of T dash and F. So at this point, I am having the value of t, which is 4, and I am also having the value of f, which is 5. So here I am going to print its value because in the production, as we already see in the previously, that in the production t produces t dash into f, the action taken is print into. So I am going to print into here because at this point I am having the value of t dash, which is 4, and having the value of f, which is 5, and now I am moving upward, and at the last I am having or I am reaching the root. So at this point, as you can see here at the root, I am having the value of e, which is this, which is 3, and also I am having the value of this t, which I evaluated from the t dash into f. So at this point having I am writing the action corresponding to this production. So the action corresponding to this production is print plus. So now, as you can see here, that if you follow this path, then the paths, then the output is firstly we have the 3, then we have the 4, then we have the 5, and after that we get the into sign, and after that we get the plus sign. So the output is 3, 4, 5 into and plus. So I am encircling the output here. All of you clearly see it. So just 5 minutes are remaining. So all of you understand it? So how we are going to calculate it and how we are going to convert the infix expression to the postfix expression by using such type of grammar, because in the previous unit of syntax analysis we are only having the grammar, and we only from that grammar we are going to produce or generate the parse tree only. But in semantic analysis, uh, we have the grammar, and corresponding to that grammar we have the semantic actions corresponding to their to each production. So we are using the semantic actions as well in order to solve the numericals which are based on the sentence directed translation. So I think that's it for today's class, because only 2 minutes are remaining. So we are going to continue this concept, and some more numericals which are based on this concept in our next class. So thank you very much for today's class, and you can leave the class. I am providing you the notes of this class uh, on your mail. So just thank you very much. Now you can leave this meeting.